Okay, and welcome to our online training. Okay, so we are going to continue with our lectures on leveling. The last class we gave some theoretical concept on leveling and its application. Today we are going to work on some. Today we are going to work on some exercises. But before going to the exercises and the solutions, we are going to have a rundown of the literature we made. We gave the introduction to leveling. We said leveling is a fundamental survey technique used to determine the elevation of point. So we can have points on the earth surface, maybe in a terrain. We can have point on the earth surface. Let's say we are carrying out a project and we want to know the height or the height difference between this point. We use leveling technique to do this. Assuming that we have a point here, let's say we have a point A, and we have another point B. To know the height difference between A and B on the site, we use leveling technique. Leveling technique permits us to determine height of point. And now, the objective of leveling in civil engineering, we have earlier talked on establishing elevations. Elevation is also a synonym of height of point. It's also a synonym of reduced level or spot height. So we use it to determine spot height of point on the site. Then when we have obtained the spot height, we can now realize a contour map. A contour map is very useful. Let's say we want to realize a project in the east and the architect happens to be in the west. Just with the aid of a contour, just with the availability of a contour map given to the architect in the east, he can understand or he can see the physiognomy or the topography of the site using the contour map. So from that topography, he can now interpret how, from the contour map, the architect can interpret how the site looks like. He can now, that will permit him to conceive plans that can adapt to the site. Also, we also use it when we are doing some work like foundation, where we control depth of foundation digging. We also use leveling technique to, you know, for volume of earthwork, etc. So these are the application of leveling. We said drainage and grading design. We have drainage system. If we are working a project on a site, we can do some sort of analysis, water flow analysis in a software known as Civil 3D. As long as we have the spot height of point spread on the site, we can now do water flow analysis to see if rain falls, the zone or the path that water will likely flow. So we also use it on monitoring ground movement, height of point, like bridges, they use it to monitor the ground movement of structures, engineering structures. Road and highway design, yes, road and highway design. We use leveling technique to study the gradient or what they call the longitudinal profile of the natural ground. We also use this leveling technique to calculate volume of earthwork that will be involved in the whole project, cut and fill. Then here now we have the instrument used for leveling. We have the automatic level. This is an image of automatic dumping level. We have the digital level. Those are instruments that we use when doing direct leveling. Then here we have the automatic level that has been mounted on a tripod. Then if we look on our right, we have what they call staff, a graduated staff. So this instrument, this graduated staff actually gives us site readings of point on the site. So this is the automatic level and the part of the automatic level label. So we have the side, we have the circular level bubble, we have the objective lens, etc. So now what we are seeing here is actually a total station. Mark Laker, there are several types of mark. We have high target, we have Laker, etc. etc. This total station and the total station is used to carry out indirect leveling or trigonometry leveling. Now, the indirect leveling, when we are working on the side, where it's mostly used on the side that is mountainous, on mountainous side. Or if we are carrying out a project where we want to do what we call tachyometry surveys, we want to represent the planimetry, the altimetry, and at the end of the day, we want to consider the three-dimensional perspective of the terrain. Yes, so we use data station to do that. And here we have the data station and its part. We have the tripod, we have the prism pole, and we have the charger. Okay, here we are talking about type of direct leveling, and the definition of direct leveling has been given. Definition of indirect leveling has been given, or trigonometry leveling. So we are told the first type of direct leveling is differential leveling. We see we have a point BM1, we have another point BM2, and BM1 and BM2 happens to be benchmark 1, benchmark 2. Those are points whose the altitude or elevation have been determined with high precision using geodetic method. Then now maybe we want to determine the height of points in between these 2 points BM1, BM2. So these are point one, these are another point two. So what we do is with differential leveling, we station approximately midpoint between BM1 and the first point. We take the backside reading, we take the foreside reading. With the backside reading and the foreside reading, we can have the height difference between BM1 and the first point. If we know the height difference, if we know the height of BM1, of course, we can calculate the height of this first point using the rise and fall method. Then after now, we displace the instrument to the second station, then we displace it to the third station, and so on and so forth. Yeah, this is another instrument. This is another differential leveling or line leveling. This is another cross section of a line leveling or differential leveling where we see the backside within foreside within have been taken right up to another known point. Yeah, we are talking it's procedure for differential leveling. Now we are talking about the procedure for differential leveling, how we are going to set up the instrument midpoint between point, take side readings. Yeah, take side readings, the back side, after we are going to take the foresight. After we are going to use the rise and fall method to calculate the height difference, like backside minus foresight, it gives us the height difference between A and B. Now, if we happen to know the height of A, we can now calculate the height of B, which should be equal to height of A will be equal to plus or minus. This is plus or minus, with nowhere draft. Plus or minus height AB. This plus or minus simply means if we take backside minus foresight, we can either have a negative value or we can have a positive value. Now, this is our exercise. Now, example one, calculation of height of natural ground using the rise and fall method. During a road project, it determines spot height of point along the center axis of a proposed corridor for a road project. During a road project, it determines spot height of point along the center axis of a proposed corridor for a road project. Now, there was a road project, and a corridor was proposed for the road project, and they want to determine the height and the height of point along the center axis of this corridor that has been allocated for the road project. Actually, the project starts on point A and ends on point F. On point A, we have a benchmark whose height is 150.761. On point F, we have another benchmark whose height is 152.675, sorry, 676 meter. And now series of points were placed in between with regular interval were placed between point A and F. And I want us to determine the height of this series of points. Now, this is the sketch of what was happening. This point A, HA, and this point HF. the last point here. And these are the point we did so many instrument setup, ST1, ST2, ST3, ST4, and ST5. And we took point B, C, D, right up to the last one, right to E. And these are the right where they are ratings, backside, foresight, backside, foresight, backside, foresight. You are seeing 1,746, 1,621, 1,720, 1,610, 1,910, 1,211, 1,432, and so on and so forth. Now, these are the side reading that have been tabulated. These are the side reading that have been tabulated. When we collect data in the field, we have to tabulate the data. If you look there, you will notice that station, backside on the point, backside in millimeter, foresight in millimeter, rise in millimeter, fall in millimeter, adjusted height difference. So they adjusted rise and fall in meter, then they reduce level the height of point, then the point. Now you're going to notice that with station, the first position was ST1 was between A and B, and we have ST2, and this were the readings we took, the backside reading, the foresight reading. After that, we did a summation of the backside. It gave us 8,814. We did a summation of the foresight, 6,904. Of course, we know that we are using the rise and fall method. We know that to calculate the height of each point, we can take backside minus foresight. Let's say we want to know the height of point B, the height of point B here. We take the backside minus foresight. It's going to give us the height difference between A and B. Knowing the height difference between A and B, we can now calculate the height of point B, isn't it? Because we already know the height of H. HA was given at 150.761. We can now take 150.761 plus the height difference, which is the 0.125, isn't it? It will give us the height of point B. But we are not going to go directly to start calculating height of point. We have to verify, we have to do a check. We have to verify, we have to do accuracy assessment. We have to verify if maybe we have made an error when collecting data in the field. Because in engineering, when we're dealing with data collection, we don't just collect data and start using it. We have to check the data. We have to do some sort of accuracy and accuracy assessment. That means we have to calculate the error, and we have to calculate the tolerance, and we have to compare the error and the tolerance. If the error is superior, delta H, if it is greater than the tolerance, then the work will be rejected. But if the error is less than or equal to the tolerance, then the work is good. We can proceed with our calculations. Now, how can we calculate error? We can calculate error by saying delta H equals to HAF practical minus HAF theoretical. What is HAF practical? HAF practical is a summation of backside. This, you remember that this and the HAF stands for height difference between A and B. A and B, that's the first point, and the last point, the height difference practical. So the practical will be the summation of backside minus summation of foresight, which this is the formula here. So if this is the summation of backside and this is summation of foresight, we are going to have 1,910 millimeter. Then now, what is HAF theory? HAF theory now will be the height of the height difference between the height that has been calculated with high degree of precision. That's like with the rotating point. For example, we have here on point A, we have the height that was given, and on F we have the height that was already given. So when we take the height difference, we are going to know we take the two, we take their differences, HA minus HF. We are going to know the height difference theory. Now a little bit on the concept of theory and practical. We all know that the sum of angle of an interior triangle, the interior angles the sum of angles in an interior triangle is 200 degrees or 180 degrees. So we can say theoretically the sum of angles in an interior angle is 180 degrees or 200 degrees. But if we happen to come with an instrument, let's say a total station, to measure the interior angle of a triangle, it will be impossible for us to have 200 degrees. We might have 200.005, or we might have 199.9922. So the difference now between 199.9922 and 200, that difference is the error. That 200.005 minus 200, That minus 0.5 is the error. So now the error can be seen as insignificant or can be seen as significant if we compare with the tolerance. So that's just a concept about error. Now our delta H, our error now is 5 millimeter. Now let us calculate our permissible error. Our permissible error known as delta perm will be plus or minus 2.7.1 millimeter multiplied by 2 millimeter multiplied by the square root of 2 multiplied by the square root of n now. So this one we did not put a plus or minus. There's a plus or minus in front of 2.7. So the formula is plus or minus 2.7 multiplied by 1 millimeter multiplied by the square root of 2 multiplied by the square root of n, where n here is the only variable and n stands for the number of stations. So we are going to have theta pem, which will be plus or minus 2.7.1 multiplied by the square root of 2 multiplied by the square root of 5, because we have 5 stations. So it's going to give us approximately plus or minus, place in front of this plus 9, we're going to have approximately plus or minus 9 millimeter. Yes, approximately plus or minus 9 millimeter. Yes. So when we look at the error, we have an error of minus 5 millimeter, and we have a tolerance of plus or minus 9 millimeter. That means our error is less than the tolerance. That means our work is good. We can proceed with our calculation. Now, if you look down, you're going to see something like correction. There is an assumption that despite the fact that the error is less than the tolerance, there is an assumption that maybe that error of 5 millimeter was generated by one single point or two single point. Now, to make the error becomes more insignificant, what we usually do is we spread the error to the entire work. We now say correction will be equal to minus delta H divided by n, minus delta H divided by 10, where minus delta H is the error and that n is the number of stations. So we are going to have plus 1 millimeter. So when you look now on our table, we are going to see that and plus 1 millimeter has been added to the height difference that we obtained, plus 1 millimeter. So if we take 125 plus 1, we're going to have 126 millimeter. Convert it to meter, we are going to put it on the table of adjusted height difference. Same thing here, 110 plus 1 millimeter, we're going to have 111. Convert it to meter, we're going to have this just like that, even here, right like that. So that's how we do to have the adjusted height difference. Now that we have known the adjusted height difference, with the height difference, we can now proceed to calculate the height of the different points. To know the height of point B, we already have the height of point A. To know the height of point B, we simply took height of point A plus the height difference. Now that we know the height of point B, to know the height of point C, we simply took height of point B plus the height difference. To know the height of point C, we simply took height of point C plus the height difference, and so on and so forth, right up to the last point E. Okay, thank you very much. Thank you very much. And one thing that I would like to also mention before we close the class is that here in the here in this level, this method of calculating on the theoretical height difference, which we say we take the first initial height minus the last height. You know, in a close, this one is done in a line leveling. In a close leveling, that's a leveling that we have. We was done with the close leveling. That's in a polygon, a close side. The theoretical height difference is zero. Why? Because we start on a known point and end on a known point. If we say we are starting on point A and ends on point A, we go around like a polygon. Let's say like a closed polygon like this. Let me see how I can. Let's say there's a closed polygon like this. This is a closed polygon now. We put that this is point A up here. We survey. If we say that this is point A here, we survey, we go around and end on point A. So if point A is 100 meter, if the HA is 100 meter, we say 100 meter minus 100 meter. At the end of the day, we're going to have zero. So the theoretical height difference in the closed polygon is zero, or in a closed leveling is zero. Thank you very much. So the next class we'll be talking about on the profile, how to do profile leveling. Sorry, yeah, profile leveling and how to design work profiles.